everyone. So I'm going to continue on with our discussion of forces, and in particular, we're going to start our discussion about Newton's laws of motion. Now, I had mentioned before that Newton, well, you should have known about how Newton came up with his idea of the three laws of motion from the whole Apple shtick. The story goes that he got hit on the head, and instead of thinking what everyone else thinks, he kind of started taking that and thinking, why do objects move? What causes them to move differently? And I had mentioned before that this led him to basically develop his understanding of forces much greater than what we saw before. This led him to uh, bring about the discussion of what gravity is and basically come up with the idea and the concept of these invisible forces that act on objects. And also came up with calculus and math and basically revolutionized all of physics for years and years to come. And it's only until recently that we've been able to make improvements based off of improved technology. Because of this, we actually called this level of physics Newtonian physics after him. Basically, Newtonian physics is everything up until the modern era, which is essentially around the 1900s, where we started developing, getting enough technology to go at the microscopic or far below the microscopic level, as well as out into the planetary scale. And that's where we end up finding out that Newton's laws actually end up failing at these extreme cases. And that actually led us to finding things like quantum physics and relativistic physics. But for the most part, at the human scale and everything that we would experience, Newton's three laws of motion are the foundation for it. A lot of equations that we're going to learn later on and a lot of other laws that we're going to learn basically come back to the concept of Newton's three laws. Um, so we're going to focus on the first law right now. So the first law basically kind of explains why objects move the way they do. What is needed in order for an object to move is essentially the idea. Now, you've all heard these laws before, but I want to actually explain what they mean. So Newton's first law is split into two separate parts. The first is an object at rest tends to stay at rest unless acted upon by an unbalanced force. And the second one, an object in motion tends to stay in motion, moving at a constant velocity unless acted upon by unbalanced force. Basically, uh, to kind of whittle this down into simpler terms, what this really means is that an object will continue doing whatever it's doing. It will continue in its restful motion. It will continue in its straight motion unless you give it a force, unless you force it to do something else. Objects are resistant to changing their motion. They're resistant to uh, um, changing the direction of their velocity or changing the value of their velocity or even getting one to begin with. And they won't do it unless you provide a force. This law it actually has a lot of parts to it, but this actually leads us into this idea of inertia. In fact, the first law is usually called the law of inertia because it kind of revolves around this central idea. So inertia, if again the sciencey definition would be an object's resistance to the change in motion. The idea being that an object with a high inertia is more resistant to changing its motion, requires more force in order to move it. So if we look at two objects, let's say one of them is a tennis ball and the other one's a bowling ball. One of those objects is going to be more resistant to changing motion. If they're both at rest, one of them is going to require more force to get it to move and to even get it moving as fast as the other one. If they're both moving, one of them is going to require more force to stop that motion. And we all know that that's the bowling ball. The bowling ball is the one that has more inertia. We can basically go around and keep trying to think about what objects have the higher and lower inertia, but what it comes down to is inertia is just mass. Inertia is just a fancy, sciencey way of saying the term mass. Objects with high mass have high inertia. So a bowling ball has a higher inertia because it has a higher mass. Uh, this also leads us into the idea of why we end up using wrecking balls in order to demolish buildings and why we use anvils to bend metal, because it kind of goes with that same idea. When we have a wrecking ball, the big, massive metal sphere, and we swing it into the wall, basically what's happening is we're moving the object. We swing it up into the air, give it some initial motion. That wrecking ball, because of its high inertia, will continue doing what it's doing, moving forward. Uh, and it'll be very resistant to stopping that forward motion. So when it comes into contact with a wall, that wall will have to provide a large amount of force to stop the bowling ball's forward motion. Because the force required to stop that bowling ball is so high, the wall cannot provide it, and that causes it to basically collapse under the motion of the wrecking ball. And that results in the wrecking ball basically continuing on in that motion, plowing right through and breaking down the wall. If we changed the wrecking ball into something lighter, like maybe a giant teddy bear, then the teddy bear won't have enough inertia to plow through the wall and will actually end up bouncing off of the wall. So, and that's because the wall will be able to provide enough force to stop that forward motion. Going to the anvils, so if you've ever seen video clips of people, doing metal work, they always do the work on top of this giant, basically giant slab of metal. And again, it's the same idea. You're constantly hammering down on metal, providing a downward force onto a surface. If you're doing it onto a lighter surface, that surface is going to be constantly bumping up and down, moving, because the force that you're providing will be able to move the surface underneath you. You don't want that when you're bending metal, so you get this giant metal slab, so that all that force that you provide is not going to be enough to move the anvil, allowing you to have a nice, sturdy surface to work on. So again, this is kind of like one of the ideas that objects are resistant to change its motion. This change in motion or this resistance is based off of its mass. The more mass it is, the more force is required to change that motion. This is a clip from, I remember, a commercial back when I was younger that I remember seeing it. You can look online for it. Basically, it's the same idea about replacing a wrecking ball with a giant teddy bear. All right, here are some uh, ironic pictures. One thing that I want to point out about this is actually pretty much the reason why it's important that when you're driving in a car that you have a seatbelt on. So this law is actually kind of the reason for that. When you're driving in the car, even though it doesn't feel like it, you are moving. You're moving at 60 miles an hour because the car is moving at 60 miles an hour. If you stop your car suddenly, Newton's first law says that your body will continue moving forward with that speed. So your body will move forward unless some force is provided to stop you. If you're smart and you have a seatbelt on, the seatbelt is going to provide that necessary force. Depending on how fast you're going, maybe an airbag will actually deploy as well to provide an additional force onto you to stop you. But if you don't have an airbag or you don't have a seatbelt, the thing that's going to end up providing you that force that stops your forward motion will be the steering wheel or your windshield or the wall behind your windshield. So you always want to make sure that you have your seatbelt on so that you have a force that can be provided in case of a short stop to stop your forward motion. It's also one of the other reasons why you want to make sure that you have items. If you put stuff in your car, you want to make sure that items won't end up moving forward or moving backwards or moving around as you're in the car, because if you're driving in the car and you have a dresser or something in your back seat or in the bed of your truck, when you stop forward or stop short, or even if you start accelerating, that object, because of Newton's first law, will end up moving in a certain direction accordingly, and it may fall off your truck or slam into a glass, and you might end up breaking it or breaking something in your car. So you want to always make sure that things are basically stable, so that there's something that can provide the necessary force to change that object's motion along with the car. This picture actually also reminds me of a interesting video clip that I remember watching from the show called A Thousand Ways to Die. In it, a person had a coffin in the back seat of their van. They stopped short. The van, because the coffin wasn't properly secured, it moved forward. Again, an object in motion tends to stay in motion. It continued moving forward even though the car was stopped because there was nothing to provide that unbalanced force, and that resulted in the coffin slamming into the person's head and killing him. So again, make sure that things are strapped down when you're driving, because Newton's first law says a force is required to change that object's motion with the car. All right. So here's a first question. Pause the video, works up. I'm going to go over in a second. All right. So the question says, which of these has the greatest inertia? Well, as we mentioned before, inertia is just a fancy way of saying mass. So the answer is number 4. Now, this may seem really easy, but this will actually get a little bit trickier as the year progresses and you start learning more information. Because if you notice, they give you velocities, and they do that for a very specific reason. The definition for inertia and the concept of inertia is actually very similar to another concept called momentum. And in momentum, you take into account both the mass and the velocity. So the trick here is that they're expecting you to instead use the velocity with the mass and find the momentums, and accidentally misread this as wondering which one has the greatest momentum rather than the greatest inertia. And they always set it up so that the one that has the greatest inertia never has the greatest momentum. In fact, this is the one with the greatest momentum. Right. There's a second thing that actually is extremely important from this law, and it's this idea of equilibrium, state of balance. You've learned this in other classes. You've definitely heard the term equilibrium plenty of times. You've heard it in chemistry and bio, and in all the cases, it's the same. It's an idea of balance. In this case, when we use the term equilibrium, we're referring to the balance of the forces. So again, the law states that there's a change in motion if the forces are if the forces are unbalanced. That means that if the forces are balanced, then the object will continue doing what it's doing. In particular, either being at rest or moving in a straight line at a constant velocity, and it won't change that motion. So what we can take away from this is that if the forces are balanced, then the object must be in a state of equilibrium. And if the object is in a state of equilibrium, we know that it is either at rest or a constant velocity. Basically, the only thing that we don't know which of those two it is without any extra pieces of information, but we do know that it's not accelerating. That's essentially the idea. So, um, this is going to be a very important aspect when you're doing problems. You're going to want to constantly be aware of the phrases at rest, constant velocity, equilibrium, um, balance forces, whatever they say, because all of these are going to really make the problems easier, because you'll know that if you have a force of 5 newtons to the right, well, there has to be a force of 5 newtons to the left. So if you're trying to figure out what that force going to the left is, it's now 5 newtons, because Newton's first law says if the object is at rest or moving with a constant velocity, it must be in equilibrium. Now, this also leads into, I think this should be the last thing about that we can get from Newton's first law, which is this idea of net force. So we've talked about all the forces acting on an object, gravitational force, normal, tension, all that stuff. The net force is essentially the resultant of these forces. Remember, forces are vectors. So that means that if we have multiple forces acting on an object, what we can instead do is just talk about what the resulting force effect is. It's not really that important to know that there's all these individual forces going left and right, it's better to know that, well, in general, the thing that it's actually feeling is just one single force to the right. So, what we're going to end up doing is talking about this net force a lot. The net force is a vector sum of the forces. You might actually hear me constantly refer to it as adding the forces. Um, just realize that it's a lazy way of me saying the vector sum, because if the forces are in the same direction, we add them, but if the forces are in opposite directions, we're going to subtract them, and if they're perpendicular, then we do Pythagorean theorem. Now, it's important to note that just like with the projectile motion topic, motion in the y and motion in the x are independent of each other. So that means that the same thing is going to have to apply for forces. When I have forces acting on an object, I'm going to have to look at the forces in the x direction and the forces in the y direction individually and take the net force in those two directions. Now, if the sum of the forces, I should have been a little bit more clear here. This should have a summation sign. The sum of the forces in the x and the sum of the forces in the y. If those both equal zero, then the object is in equilibrium and we have a net force of zero. So basically saying that if in all the directions the forces are balanced, we're in equilibrium. Now, if only one of these is zero and then the other one isn't, then the object's not going to be in equilibrium. We don't actually make that comment, so try to avoid that. There's going to be a lot of cases where you'll have an object, I'll try to draw it here, where it's got 5 newtons going up, 5 newtons down, and then 3 newtons to the right. You might be inclined to say like, oh, it's in equilibrium vertically. You try to avoid saying that. Typically the equilibrium state is in total, like the entire situation, not just one of the dimensions. But yeah, so what we end up getting here is that the net force ends up equaling whatever the non-zero force direction is. So if you have a net force in the x direction, that's what your net force in total. If neither of them are equal to zero, so the sum of the forces in the x and the sum of the forces in the y end up with some number, then once again it's not in equilibrium, and what we're going to have to do is use Pythagorean theorem to figure out what that net force is. So we'll figure out that there's a certain amount of force going to the right, a certain amount of force going vertically, Pythagorean theorem to figure out what the resultant force, the total net force, is. All right. So pick the situations that describe equilibrium. Some of these have multiple choices. Pause video, work itself, and we'll go over in a second. All right, so for part A, well, for all of these, what we want to do is go back to the idea of what it means to be in equilibrium. If an object's in equilibrium, it's either at rest or constant velocity, and it is not accelerating. Those are the three main things. So part A says an object or a ball is dropped from a building. We know that this can't be true because all objects falling in the air experience acceleration equal to the acceleration of gravity. And by extension, B also has to be thrown out for the exact same reason. It doesn't matter if the object's dropped or thrown, they're both accelerating because of gravity. For part C, or choice C, it says the kid is increasing in speed. Well, that's an acceleration, so that gets thrown out. Choice D says the car is on a highway with cruise control. If you don't know what cruise control is, that basically means that the speed of the car is not changing. And it doesn't explicitly say it, but it's moving in a straight line. So this is actually ends up being a situation that's in equilibrium. So let's look at the other cases. For part E, a book is sliding to a stop. Well, again, it's not at stop yet, it's going to stop. So that's a deceleration. That's not right. Choice F, the stoplight is hanging from a cable. This is just like a typical stoplight if you looked at it from a car. This is at rest, so this one's also in equilibrium. And then we get to choice G. The Earth orbiting the sun at a constant speed. Now, a lot of people will immediately pick up on the word constant speed and believe that this is in equilibrium, but it is not. This is not in equilibrium. Now, you might be wondering why. If you recall, the previous definition I gave was that an object is in equilibrium if it is at rest or at a constant velocity. The reason this is important is because speed and velocity have one small difference. Velocity implies direction. So, if we say Earth is orbiting the sun at a constant speed, the Earth is not moving in a single direction. It is constantly moving in a circle, changing the direction of its velocity. Therefore, even though it is constant speed, it is not a constant velocity. So G is not one of these cases. Um, Keep an eye out for that, because if you ever see a question like this of which one's in equilibrium, um, that one always gets thrown in there as like a trick for you to kind of immediately pick up on the constant speed aspect and pick it out of, you know, a reaction. All right, here's the next question. Pause the video, work itself. I'm going for a second. All right, once again, we're looking for a box that's in equilibrium, meaning all the forces on it are balanced. So we have these two forces are equal and they're balanced, but there's an unbalanced 5 newtons down. That one's not it. This one has the 2 newtons balanced, but vertically there's a net force of 3. This one, even though all the numbers add up to 5, they're not balanced. There's a net force in the horizontal, net force in the vertical. So that means that my choice 2 is the only one in equilibrium. All right. It's actually extremely important, kind of going back to what I said before, that you draw FBDs in order to determine if an object is in equilibrium or not. Like I said, if an object's in equilibrium, the FBD really kind of ends up falling into place because you'll just see, oh, we have a force down and we have a force up, they have to be equal. We have a force to the left and a force to the right, they must be equal. I kind of talked about these. These are very common forces that pop up. Honestly, when I went through the previous video of all the different types of forces, I kind of gave them in the order of most common. So basically, you should be kind of going through these forces in your head. One, you're drawing an FBD. Um, yeah. And that's basically it for Newton's first law. Like I said, it's one of those really important foundations for the force aspect. You know, the idea of equilibrium is extremely important, and knowing when an object's in equilibrium and when it's not in equilibrium. Later on, we'll talk about Newton's second law and basically how we can kind of piggyback off of the first law's comment about the idea of accelerating if the forces are unbalanced and see what that actually means. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.